Welcome back, and let's start looking at our electrophilic addition reactions, which is the next in a series of reactions that we need to know for HL chemistry. Essentially what we're looking at now, when we say electrophilic addition, this is the standard addition reactions that we've looked at prior to HL, where we said that we could add Cl2 across a double bond, HCl across a double bond, etc. We know that the carbon in an alkene will have a trigonal planar shape, okay, because we have the electron domain geometry here where we have 1, 2, 3 electron domains or 3 negative charge centers, the double bond forming 1, and that gives us a 120-degree bond angle approximately around this carbon. This means that the structure is largely open. Because of its planar nature, it's largely open to attack from above or below, and the bond remains open to attack from different species. The pi bond we can think of as an area of electron density. Remember that we have the overlap of the p orbitals forming the pi bond, and that we have electrons being shared in that space, in that newly created bonding orbital. So this means that that rich electron dense space is going to be attractive to electrophiles. Okay, so electrophiles are the opposite of a nucleophile, that being that an electrophile will be attracted to an electron dense center. It's electron loving. And electrons in the pi cloud are less closely associated with the nuclei, so they're less tightly held. So they're going to be easier to pull away, to break apart, and to form a new bond with, which is exactly what we see in our addition reactions. So just remembering the last look that we looked at with ethene, in that we had the two s and p orbital overlap here. So we've got the two p orbitals overlapping, and then we have these sigma bonds here and the sigma bond here. Remembering that we have the pi bond formation across our p orbitals. So with electrophilic addition, the electrons in the pi bond are going to be attracted to the delta plus of a polar bond. Okay, so when we have electrophiles, they are electron deficient species. Okay, so we have to have a partially positive charge, okay, on these, or a positive charge. They are positive ions or polar molecules where we have a partial positive charge. So something like HCl, where we have this disruption in the electron density with the electrons moving towards this now can act as an electrophile. They will form bonds by accepting the electron pair from the electron-rich center. So we can see electrophilic addition where we see the addition of halogens and hydrogen halides to alkenes to produce halogenoalkanes. We look at this, one of the ones that we should be familiar with by now is the bromine test in order to determine whether a hydrocarbon is saturated, remembering that our Br2 liquid is going to be a brown or orange color. When it reacts, it decolorizes. Okay, decolorizes the bromine, so we lose that brown-orange color as the bromine attaches across the double bond. This mechanism is going to start with bromine, which is non-polar, becoming polarized as it approaches the double bond. So as the bromine approaches the double bond, we can see here that the electrons in the double bond repel the electron pair away from this bromine, making it a little bit more positive in comparison to the other one. The electrons then, remember curly arrow notation, the electrons will come from the double bond to the bromine, and then this repels the electron pair in the bond out onto the other bromine to form the bromide anion. Bromine is polarized by the electron-rich double bond, so the Br atom closest to the double bond gains the slightly positive charge. It splits heterolytically, so we get a Br plus, which is very unstable, and a Br minus. The Br plus will attack the double bond and attaches to it, which leaves an unstable carbocation intermediate. Okay, so we have the heterolytic cleavage of the bromine with the approach that causes it to polarize. The bromine attaches to one carbon, okay, because remember we've got a curly arrow coming out here too. So the bromine attaches to one carbon, leaving the carbocation intermediate and a bromide anion. The bromide anion then will actually reattach this electron deficient center and form the final di-substituted product. So this initial step is our slow step, and then we have a fast attack of the bromide anion with the carbocation intermediate. If we look at this with things like hydrogen bromide, our hydrogen halides, we have a similar mechanism where we will have a partially positive hydrogen and bromine, so we get a heterolytic attack. The electrophile here being attacked by the electron-rich electrons in the double bond. So the electrons will come out from the double bond onto the delta positive, pushing these out onto the bromine to form the bromide, carbocation intermediate, which will then react quickly to form the bromoethane. This means that depending on whether or not the hydrocarbon is symmetrical, there may be different products that are formed. So if we look at propane, which is an asymmetric alkene, i.e. the double bond is not in the middle of the molecule, so which end the hydrogen or the bromine attaches to gives different products, we can end up with two different carbocation intermediates. We can end up with the carbocation forming on the terminal carbon, which would give one bromopropane, or the carbocation forming on the second carbon in the chain, which would give us two bromopropane. Of course, there are rules for which gives us the most common product, and these apply from the inductive effects that we learnt about in our SN1, SN2 mechanisms. Okay, so remembering that alkyl groups attached to the carbocation will have an inductive effect. So we have primary and secondary carbocations in this case, and the secondary will be more stable due to the two inductive effects from the alkyl groups on either side. Because these alkyl groups push electron density away from themselves to lessen the density of the positive charge, if we have alkyl groups next to the positively charged carbon, they have what we refer to as a positive inductive effect, a stabilizing effect. This means that a primary carbocation is stabilized by only one positive inductive effect. A secondary carbocation is stabilized by two inductive effects. So the stabilization in the secondary cation is greater, so the mechanism that forms the secondary carbocation will be preferred. Okay, so in this case, we can see this is what we get from one bromopropane, because we would have the carbocation forming, because remember it's going to add, so we have the carbocation forming in this region here because we've broken the double bond. So we would have the carbocation forming on here, and the hydrogen would attach here. Okay, and then the secondary carbocation is going to be where we had two bromopropane, because we have the carbocation forming on this one and the hydrogen adding to the terminal one, remembering that the hydrogen adds across the double bond first, and then the bromine will attack the carbocation. So essentially, these are the two mechanisms that we're looking at. The electrons will leave, attach the partially positive hydrogen, pushing the electrons onto the electronegative bromine, creating the secondary carbocation, and then this is the formation. Then from there, we have the attack from the lone pair into the positive carbocation center, forming two bromopropane. This is the preferred product because of the higher stability of the carbocation. Markovnikov's rule is what we use to predict the outcome of an addition reaction for any hydrogen halide for an asymmetric alkene. The simple rule is that the hydrogen will attach to the carbon that is already bonded to the greater number of hydrogens. Okay, so that will give the greater inductive effect to the other carbon, which is going to be where our carbocation forms. So the whole Markovnikovs rule is based on the fact that this type of mechanism will produce the most stable carbocation. So the more electropositive part of the reacting species bonds to the least substituted atom in the alkene. So if we've got a delta plus, delta minus in our molecule, then the delta plus initial bonding will bond to the least substituted species, leaving the most substituted to be the carbocation. So if we have a look at this worked example, we're asked to write the names and structures of two possible products of the addition of the interhalogen compound BRCl. So we've got two different halogens to propene. We need to consider which is likely to be the major product and explain why. So when we look at this, there's clearly going to be two ways that we can consider the attack. And the first thing we need to consider which is going to be the more electronegative out of the two halogens that are in our compound. So when we consider this, we know that chlorine is going to be more electronegative than bromine. So we're going to have our delta plus on the bromine and our delta minus on the chlorine. So let's look at this in detail. What we have are two possible reactions where we have the attack of the double bond towards the partially positive towards the chlorine, and then that pushes out the bromine, which would give us initial attachment of the chlorine on carbon 1, and then the secondary attack of bromine onto the carbocation. Or we can have the attack coming from the double bond to the bromine, pushing out the chloride ion, and then the chloride attacking at the carbocation. So we need to decide which one of these would be more likely, remembering that the more electropositive attaches to the least substituted carbon, which would be carbon 1. If we remember from our periodic table, chlorine is closer to fluorine, chlorine, or even our electronegativity values. Chlorine is more electronegative than bromine. So our polarization, as we were talking about before, means that we have the delta plus and the delta minus, which means that this is going to be the first one to attach and will attach to the least substituted carbon. So we can see here that we should end up with this one being our main product, because this means that the bromine will leave a secondary carbocation available for the chlorine to attack, and the bromine is the least electronegative. So that means that the secondary carbocation for the formation of the bromine, leading to the synthesis of 1-bromo-2-chloropropane. So we will see this one being formed as the major product because we have the more electropositive halogen doing the initial attachment, so that the second one is attaching to the more stable secondary carbocation. That's it for electrophilic addition. We'll do some practice in class, and I'll see you later.